Hello and welcome to Menan Buttes. More specifically, this is North Menan Buttes. Menan Buttes is a cluster of about 6 or so volcanic vents, with North Menan Butte and South Menan Butte being the largest of those vents. And we're going to take a hike up this thing, explore the summit area, the crater, and the geology of the area, and help you piece together the fascinating story of how this volcano came to be. This is one of the volcanoes out here in the Snake River Plain. We're in eastern Idaho, and now we're looking across the Snake River Plain at the Lemhi Range and the Beaverhead Mountains and the Lost River Range as well. So thanks for joining me on this beautiful morning. Geology professor Shawn Willsey. And again, we're going to take a hike up here. It's about 3/4 of a mile, maybe about a 700-foot ascent in elevation. And this is just one of my favorite places in eastern Idaho. It's a great place for a hike, but also has some really fascinating geology. Once we get on top, we'll get a great view of the crater, South Menan Butte, the Snake River below, and we'll piece it all together. So join me as we hike on up the hill and explore North Menan Butte. Okay, team, worked my way partway up North Menan Butte. You can see the parking lot down here. I don't know, maybe come up about 500 feet, 160, 70 kilometers, something like that. But a great view, a little bit of the lay of the land again. So looking northwest at the Beaverhead, then the Lemhi Range, then the Lost River Range, a series of more or less north-south trending mountains that are all part of the basin and range story, as this part of North America was stretched east-west. Blocks of crust dropped to form the valleys between those ranges, faults pushing the ranges up, and most recently the 1983 Boar Peak earthquake was just past that last range on its west side. Probably a little hard to make out here, but there's 3 distinct little bumps on the horizon, more or less due west. That's the far one on the right is Big Southern Butte. That's the tallest volcano, the tallest prominence in the Snake River Plain. It's about 2,000 feet tall. And then the other 2 look taller because they're closer, but that's East Butte and Middle Butte. Those 3 collectively are rhyolite lava domes, really interesting volcanoes. Hoping to get out there soon and do a video. And then swinging around to the south, looking at some of the agriculture fields here in the Snake River Plain. And then more noticeably, looking at some of these rocks here on the flank of North Menan Butte. So let's make some observations together. We'll get to the summit. We'll piece together this story as best we can. So hopefully you can see with the shaded lighting here, but we have some distinct layering going on. These layers are dipping more or less parallel to the hill slope and down to the west here. So we definitely have some prominent layering in the rocks. As I look at some of the outcrops beneath my feet, a little hard to tell what is going on here because there's just so much lichen growth on the top of these. So let's head over to this little face over here out of the sun and see if we can get a nice fresh exposure. Actually right here, this is pretty good, just on this little face. So let me get in here close so you can see. So a very dark rock, and whenever people bring me rocks to identify, or I have questions about places, it's always helpful to me to have the spatial context and knowing where it is. So knowing we're in the Snake River Plain in eastern Idaho, hopefully if you know anything about this area, your first instinct is basalt, that most of the volcanoes there are basaltic volcanoes. And I'd encourage you to take a good look at North Menan Butte and the other butte, South Menan Butte, on Google Earth or some sort of satellite imagery, and get different views of it from the side, kind of an oblique view, and see if you can figure out what kind of volcano this is. It's a little too steep to be a shield volcano, which is many of the buttes we see in southern Idaho. At the same time, it's not quite steep enough nor narrow and symmetrical enough to be what we call a cinder cone, a volcano where it erupts fragments of lava airborne that collect around the vent. So it looks a little different, the Menan Buttes. You might also notice, if you're looking at that now on Google Earth or some other satellite imagery, you might also notice that the Menan Buttes are somewhat elongated in a northeast southwest direction. So let's see if we can decipher some things by looking at the material here. We can see that what makes up much of North Menan Butte, at least in this outcrop, but I'm sure we'll see this elsewhere, is little fragments of rocks. And when we look at any of these individual fragments, we can see, hopefully you can tell this one's black. It's also a little bit glassy. The material in here is basalt, but it's a little bit shinier than what we typically see with basalt. We can see there's some ranges of sizes. So we've got a piece here that's maybe an inch, a couple centimeters in diameter, down to tiny particles as well. And then for the most part, what we see in terms of shape is the shapes of a lot of these fragments looks like they're pretty angular for the most part overall. So knowing we have a volcano here and seeing that we don't have intact lava, but actually fragmented material, that tells us that this was an explosive volcano. That it was tearing up the lava, throwing it out of the volcano airborne, exploding it out of the vent, and that material was then accumulating around the vent to form the material we see here. So this would be a tuff, volcanic tuff, if it was all ash-sized particles. Because we're seeing a little bit bigger ones here, this is what we call lapilli size, but we could still probably mainly call this material tuff, or you could call it a tuff breccia. If we know more about the process, we could probably get a little bit more specific with some terminology. Let's head over to this wall here, because I think I see another clue in our story. So in this lovely little shaded nook, which is nicely kind of honeycomb weathered, you can see some of the holes in it up here. Here we have a lot of the same material, but we also have some larger particles. So we can see there's big chunks of basalt, softball and even bigger sized pieces. If I come up here, I can see a few more. There's one right here, another one up there. So we're seeing angular particles, but we're seeing bigger particles than we saw just across the gully. These look a little different than the tiny pieces of basalt that I see in the actual tuff itself. So we could call these xenoliths, even though it's more or less the same rock type. But because this doesn't match and is likely to be much older, or at least somewhat older than the rock we see here, we might call these xenoliths. In this case, we could call them basalt xenoliths. And we can see that they're sort of just randomly helter-skelter in here. We can also again see some of the prominent layering with it kind of dipping towards your view there. So let's head to the summit, check out the crater, and see if we can start to piece this together. But we've got really good evidence here of an explosive eruption that's not just fragmenting its own lava and shredding it into tiny pieces, but throwing out occasionally particles of older pre-existing rocks that were probably lining the volcanic vent. So as the eruption's taking place, it's tearing up some of the wall rock, and those rocks are being thrown out along with the rest of the material as well. So we're close to the summit. We'll get back over on the trail here and head up to the summit and see what we can find. Okay, we've come maybe 100 or so feet, 30 meters from our last stop. We're almost at the summit here, but what I noticed was pretty interesting is that the layering in these rocks, which was oriented like this just a few hundred or so feet down the hill, now as we approach the summit, starting to roll over and become more or less close to horizontal. And I'm guessing we're close to the top. Again, the layering here looks fairly close to horizontal. And now we're looking across the crater, some communication towers across the way. And what we might be able to see here as we head to this far end of the crater is, let's see what happens with the dip or the layering of this pyroclastic material. Wow, So as we come over here, let's get to a good spot where you can look down the axis. Now we can see that it's steeply dipping to the right, which is to the east. And that's because we're heading into the interior of the crater. So the stuff's being thrown out of the crater, it's accumulating along outside the vent, forming the flank of the volcano. But the material that's inboard of that, or closer to the crater, actually has a dip back into the crater. So this crater here is the eruptive vent. This is the location where all this volcanic material was being blasted out of the earth when the Menan Buttes erupted. We also get a nice view. You can see some of the nice dip down here in the gully, pretty much the same as what we see here. The river in the distance, that's the South Fork of the Snake River, and I bet you can't quite make it out, but maybe if you can zoom in or pause, you actually see the Tetons out here as well, just above the horizon, the Grand, the Middle, and the South Teton, and then the big mountain to the left, I believe, is Mount Moran. So pretty spectacular here at North Menan Butte. So what's our story? So we've got this odd-shaped volcano. First of all, it's made out of pyroclastic material, not lava, so it's not a shield volcano. It's a little too broad and not quite steep enough to be a cinder cone, so it can't be that. What other kind of basaltic eruptions do we have in southern Idaho? Well, we sometimes have fissure eruptions along big cracks where lava comes out. Again, this doesn't match that. It's not erupting mostly lava, doesn't have the right geometry for it. So we need some other process here. What else could cause basaltic volcanoes, which normally in the Snake River Plain are fairly passive in terms of their eruptive behavior? What could cause it to become more explosive? If you've seen some of my recent videos from Iceland, or some from southern Idaho, because I've done a few of these as well, you might have the answer. The answer is water. If you have volcanoes, if you have magma interacting with water, the magma heats up the water flashes to steam. Now this happens fairly close to the surface. And when you turn water into steam or gas, that's a volume increase, that's expansion. And that's such a marked expansion that it shreds, fragments the lava into tiny pieces of ash-sized and lapilli-sized particles. And voila, you have the recipe for an explosive event. So we call these types of eruptions or volcanoes phreatomagmatic. So there's your fun word for the day. So a phreatomagmatic eruption or a phreatomagmatic volcano is one in which water and magma are interacting and producing explosive conditions. Now this would be a locally explosive event. You could probably watch this thing erupting from maybe a mile, maybe half a mile. That might be too close for comfort, but maybe a mile or so away. So it's still not nearly as explosive as a big stratovolcano like Mount St. Helens or something like that. So we can see the dip here again, kind of going back down towards the crater, looking right down the dip direction there, more or less dipping to the east. So this specific type of volcano is phreatomagmatic, but it's specifically called a tuff cone. Now a tuff cone differs from another similarly named volcano, a tuff ring, in how deep that water and magma are interacting. If it's closer to the surface, you're going to get a broader crater, not nearly as tall or steep, blasting out the material in a larger radial pattern. That'll give you a tuff ring. Here we have you can hear me sucking wind here. This thing's steeper. I just hiked up 700 feet. So this is what we call a tuff cone. It's cone shaped like a cinder cone, but unlike a cinder cone, it's not erupting particles of lava. This lava has actually interacted with water. It's also changed the color a little bit. So as we move over here towards the south end of North Menan Butte, we get a nice view of South Menan Butte. It's sort of sister volcano, another tuff cone just to the south. Now that one's mostly privately owned. That's why you see a lot of houses up there. North Menan Butte is on federal land. This is a national natural landmark, and so it actually has a trail up here, and so it's public access for the most part. And as we look at the rocks in here, we can see they're starting to take on a little bit more of a yellowish tint, a little bit different than the black tuff and the black lapilli we saw when I was just outside the volcano's flanks. This yellowish material here is called Polygonite, and Polygonite is an alteration product when a material that you get when you have these phreatomagmatic eruptions. It's very common. So it's more or less a mineral coating. It's altering this originally basaltic material into this yellowish material here. Again, Polygonite. But fundamentally, it's the same material. It's still a tuff. It still has some of these big blocks embedded in it, these xenoliths of basalt. And what we really want to find here is the key to the mystery would be, of course, well, where's the water coming from? So if this volcano is interacting with water, what's the source of that water? And as you look at these xenoliths, you mainly see these big pieces of basalt, but occasionally, a few spots, what you see are these rounded pebbles, and sometimes even cobbles bigger, of quartzite. Here's one here. There's another one over here. If I crawl my way over to here, we've got one there, one here. They're obviously quite conspicuous because they're a different color. In some places, they're a little bit more gray in color, but these lighter colored quartzites really stand out. And you can see they're more rounded. So the rounding of these particles obviously suggests transportation by water. So some sort of water was transporting these, and then somehow they became incorporated in the volcanic eruption that formed North Menan Butte. And so the answer to our story lies just down here in the valley. You can actually see the two major river systems that form the Snake River coming together. We have the Henry's Fork River here to the left, which comes out of the western side of Yellowstone Island Park area. And then straight in front of me, looking more or less due east, is the South Fork of the Snake River, which drains out of the east side of the Tetons, goes through Jackson Hole. Those two rivers join just beyond South Menan Butte. But if you look at this on Google Earth, you might be able to say to yourself, wait a minute, these volcanoes probably have disrupted the confluence of these two large rivers. And the water source that we think is responsible for these particles in here, these quartzite cobbles in and amongst the tuff and the breccia of this volcanic unit, would be either shallow, probably groundwater. So you've got all this gravel that's been deposited by these two river systems over the last several thousand years. And so as the magma was rising, it encountered beds of gravel, lots of groundwater. The water table would be basically near the surface, right where the rivers are. And so that would then be the primary water source that would allow this magma to interact with it. Now, sometimes when we get these phreatomagmatic eruptions, they may not last very long, because sometimes if there's not enough water, the magma can sort of seal off the water, not allowing any more water to flow into the magma and mix with it. And even after an initial explosive phase where they're mixing, if you can seal off the water, you can start to build just lava flows, right? Just more typical eruptions of basaltic lava, like what we would expect to see. But in this case, because it never got to that phase and it just kept pumping out a tremendous amount of this fragmented material. Here's a really large block of basalt embedded in the tuff here. You can see my shoe for some scale. That tells us that the magma, there was plenty of water mixing with the magma. Here's another nice big cobble right here by my foot, maybe about baseball size. So that's the story of the Menan Buttes, is that this was an eruption that took place probably right underneath or very close to the confluence of the Henry's Fork and the South Fork of the Snake River. That eruption, having ample amounts of water mixing with the magma, allowed, there's actually 6 eruptive vents here, but the South and North Menan Buttes are the two largest and most prominent, but there are actually some other vents as well. That's what led to these very large landmarks that we see here in eastern Idaho. It's what accounts for all the tephra, all the pyroclastic material that has erupted out of here. And again, the clue to figuring out the smoking gun, if you will, for the water body that was responsible for these phreatomagmatic eruptions is given with these cobbles, these embedded cobbles that are mixed with the volcanic material itself. So just a really fascinating story, a beautiful place to take a hike, wonderful vistas. Again, the Tetons, hopefully you can see that through the haze a little bit there. Mount Moran swinging around to the south, and then looking more or less west across the Snake River Plain. There's this nice eroded bowl near the top of North Menan Butte that provides really beautiful exposure of the volcanic material. Again, we can see the big chunks of xenoliths. We can see some of the river cobbles in here as well. But we can also see, I hope this shows up pretty well, you can see this little layer here. It's a little bit more coarser grained, then it becomes a little more fine. Another layer a little more coarsely grained, which sort of indicates it was somewhat pulsating, that the eruption was a little bit more energetic at times, fragmenting into larger particles, smaller particles. So there was a little bit of, I wouldn't say cyclicity, but some variability in its eruptive behavior. The other thing I hope you can see nicely here with the lighting is just how sparkly some of these small pieces of pyroclastic material are, these pieces of basalt. These are called, so if they're pieces of the lava that are being fragmented, these are sometimes called juvenile clasts. Basically, they're brand new baby, pieces of lava born on the day of the eruption that are being transported to the surface, as opposed to these older particles that were brought up during the eruption as well. So hopefully you enjoyed this little adventure today up North Menan Butte. Thanks for joining me. I love sharing geology with everyone. This has been a great way for me to break away from just teaching my students, which I do love, but this allows me to reach a much bigger audience. And so I love being able to share the Earth stories with not just my students, but the general public, anyone who's interested, who's willing to take a few minutes out of their day and spend time with me on these little adventures. So hope you enjoyed it. If you feel willing to, there's a donate button on the banner of the homepage. There's a thanks button below the viewer. And there's in the video description, there's a PayPal link. So any support you can send helps me get out to these places, pay for some gas money, spend time away from home, but doing what I love. So I would absolutely do this without compensation, but definitely any sort of support helps the cause a little bit. So appreciate you joining me. Hope you enjoyed this little adventure here in North Menan Butte. And hopefully you can come out here sometime on your own and enjoy the hike. And if not, you just got to experience a little virtual field trip with me. So thanks for joining me and have a good one.